Logan, what's up?
Doing good.
Have you ever had the queso sauce from El Cazador?
I think so.
It's really good. Chips and cheese. What a healthy lunch. That's what happens when I've got like 10 minutes between classes to grab something. So, today's just a review day. What do you got for me? What do you want to do more practice with?
I have the practice test printed out.
Yeah, we can go over whatever questions you want to from that.
'24, like dilution math.
Okay, we can totally do that. Renee, how you doing today?
Good. How are you?
I'm fine.
It's good.
So I need to open up the exam, the practice test. Give me just a second to get there. And we don't just have to do practice exam problems. If there's just a topic that you want me to make up a problem for, like an Alex topic, whatever, we're good.
What I seem to find is that some of the exam practice questions didn't have any correlation to Alex.
Maybe you can't see the correlation, but sometimes I think they all do. I think they all do.
What are the strong acids we have to have memorized again?
Hydrochloric acid, so sorry, HCl, HBr, HI, and HNO3.
HCl, HI,
HBr,
HBr.
and HNO3, nitric acid.
Perfect.
And Logan, which question are we talking about now? Number 24?
Yes.
Okay. Weird. All right, there we go.
Dr. Musk, when are your office hours today and tomorrow?
Today, 1 p.m. to 2 p.m. Tomorrow, 3:30 to 4:30. Wednesday, I still have 1 to 2 p.m. So if you haven't started your exam yet, I'm happy to go over something or other with you on Wednesday. That's fine.
Sorry, Tuesday you said 3:30 to 4:30?
That's right. And if none of those times work for you, just text me and we'll figure out a time when I can hop on with you, okay? I'm just going to download this so I can window it because using it in the browser is kind of being a pain in the butt. All right, sweet. Now I can have everything on the screen at once, which is what I want. So much fussing. Okay. So we are diluting Captain Crunch, or actually putting it into milk to shake the sugar out of it into solution. And we see that our initial concentration of sucrose is 1.18 molar. So 1.18 moles of C12H22O11 per liter. Weird that those are not subscripted. I don't know. I think maybe Jennifer might have messed with this exam, or maybe I screwed up somehow here. Anyway, you know that in chemical formulas, those numbers should be subscripted. I don't know why they're not in that formula. So it looks like we have 420.5 milliliters of that solution is diluted to a final volume of 3.32 liters to make solution B. And then 1.27 liters of B is diluted to 4.74 liters to produce solution C. So we have to figure out what the concentration of solution C is. Remember our magic dilution formula, C1V1 equals C2V2, where these are our initial concentration and volume. This is our final concentration and volume. As long as our concentration units match up on the two sides, as long as the volume units match up on the two sides, we're never going to mess up a dilution calculation.
That made Alex so much easier, and I didn't know that till now.
Yeah, so it's a huge benefit. All right, so let's check this out. If we start out with a concentration of 1.18 moles per liter, that's our initial concentration. Our initial volume, 420.5 milliliters. Our final concentration is going to be the concentration of solution B. So that's what we're solving for. Our final volume is 3.32 liters. Now, that could be a problem because that's a different unit of volume than what our starting volume was. So what I'm going to do is I'm going to use that volume, but I'm going to use it in units of milliliters instead to keep consistent volume units, all right, on both sides. So I converted those liters into milliliters. I just did it in my head instead of doing it on paper. So let's solve for the concentration of solution B. And I'm keeping more significant figures than I think I'm going to need because I'm going to round off at the end. I don't want to round in intermediate steps and then screw up my calculation. So I kept a couple more sig figs than I needed here. Now, with serial dilutions, what happens is that this now becomes the initial concentration because we're going to take some of this solution and dilute it again. So for our second dilution, my initial concentration is 0.14945 molar. My initial volume in that second dilution is 1.27 liters. Note, we didn't use all of that solution B, we just used some of it. All right, so that's our initial volume of solution B that we're using. We're diluting to make solution C, so that's the concentration of solution C that we're going to solve for. The final volume of solution C that we're making is 4.74 liters. So when I solve for my molarity of the final sucrose solution, solution C, I'm getting 0.0400 molar. Now D, for some reason, people have a hard time reading that one properly. So imagine we've made this solution. If we evaporate all the liquid away, the only thing that's going to be left over is the sucrose that was in those 750 milliliters. All right. So how many grams of sucrose would there be in 750 milliliters of solution C? So if I rewrite this test or the problem for the exam, I'd probably, instead of saying something about evaporation, I would just ask how many grams of sucrose are there in 750 milliliters of solution C? So how would I figure that out? We know that we can use concentration as a conversion factor to convert a volume of solution into an amount of solute. All right. Now, right now, my solution volume is in milliliters. I can very easily convert that to liters. So in liters, I have 0.750 liters of solution C. If I multiply that by C's concentration, which is 0.0400 moles of C12H22O11 per liter of solution. So volume times a concentration gives us an amount of solute. In this case, our amount of solute is a number of moles of C12H22O11. Now, if I have moles of C12H22O11, we know how to convert from moles of something into grams of something. We do it by using the molar mass of that chemical formula. So every 1 mole of C12H22O11, well, I've got to add that up. So 12 times 12 plus another 22.22 for our 22 hydrogens, plus 16 times 11 for those 11 oxygens. I'm getting 342.2 grams of C12H22O11 in every 1 mole. So multiplying a volume times a concentration, as long as the units match up, so liters and liters in the denominator of the concentration, a volume times a concentration gives us an amount of solute. So the amount of solute here is in moles because we're multiplying by liters times moles per liter. Once we know how many moles of sucrose we have, we can convert those to grams using the molar mass of sucrose.
This is for question D, right? Or is that C? Because
yeah, this is part D. The
molarity,
molarity, the molarity is what we already solved. So
yeah, we already got that molarity. Okay.
Of solution C, that's 6 question, right? We're just trying to figure out how many grams of sucrose there were in the 750 milliliters of solution C. That's what we're solving for now.
Oh, gotcha.
Okay, yeah, so this is part B. So generally speaking, whenever we want to find an amount of solute, we can do that by having both the volume of the solution and the concentration of the solution. Another way to think about this is that concentration is a conversion factor. In this case, we use concentration as a conversion factor to convert from a volume of solution into a number of moles of solute. We could also start with a number of moles of solute and use the conversion factor as its reciprocal to convert into a volume of solution instead. All right, so concentration is a conversion factor. What's in the denominator? A volume, in the numerator, an amount of solute, which means that we can use this conversion factor either way to convert from a volume into an amount of solute or from an amount of solute into a volume if we had to do that instead. So I'm getting 10.3 grams of sucrose. You guys getting the same thing?
Yeah.
Logan, is that helpful?
Yeah, it really was.
Sweet. That's what I'm here for. That and to eat delicious queso from El Cazador. Although that would be a pretty crummy life purpose if that was my life purpose, was just to eat queso dip. A delicious life purpose, but a crummy one. What other things can I help you guys with from the last few chapters?
So I've been really confused about what question is that? What number? It's going to be the one right above actually 24 that we just worked on.
Sure. I know the number.
I don't know if we've like gone over that like I don't know if we like went over that in like another Zoom or recitation, but I like have been like trying to find like where we went over this.
So Meadow, I've done a really bad job of captioning, topicking the last few meetings. I have to go back through and rewatch those, or at least like watch a few minutes of each one of them to figure out all the topics that we covered, and I'll put those captions in so it'll help you studying. But I'm happy to go over the question with you as well. So let's look at it. Okay, so let's talk about how to write total and net ionic equations for each one of these reactions. So we have to be able to predict the product of each of these reactions. And I have given you information about the second problem that says that silver sulfate is insoluble in water. In other words, silver sulfate is going to form a precipitate here. Okay. So how do we finish writing this equation? Well, you have to recognize what kind of a reaction this is that we're looking at. So HNO3 is a strong acid. Barium hydroxide is a hydroxide base. This is a neutralization reaction. So what are the products of a neutralization reaction? Water and some kind of an ionic compound, a salt. All right, water and a salt. So water is one of our products here. What salt are we making? What ionic compound? Well, it has to be the one that we get by mixing barium ions, Ba2+, with nitrate ions, NO3-. So since nitrate is a -1 and barium is a +2, the correct formula for barium nitrate has to have 2 nitrates in it. Now, barium nitrate is soluble in water, and water, our other product, is just a liquid. So that is the products of the reaction. We have not balanced the chemical equation yet. In order to do that, it looks like we need 2 nitrates on each side. So that's going to give us a 2 in front of HNO3. And if we're putting together 2 hydroxides with 2 H+, that means that we're going to make 2 waters. So there's our balanced chemical equation for that neutralization reaction. Are we good so far, Meadow? Does that make sense?
Yeah, kind of. I'm just like the foundations of what leads you to that answer. I'm still kind of confused about, so I have to like go back and kind of relearn or
yes,
reteach
what's
myself
the underlying principle here? How did I know that those were the 2 products? Those are all water and some kind of ionic compound are always the products that we get when we mix together an acid and a hydroxide base.
Gotcha. So that's just the bottom line. Okay.
Yep.
Dr. Musk, where would that information be? Like, I mean, I think I've watched all the recitations and I don't remember talking about that.
I think we talked about it in chapter, hold on, I just got done with my 161 class, so I don't remember what your chapters mean anymore. But it's really crappy because in 161, in our other book, we covered the first 9 chapters of that book too. And they're different things, which means that I have no idea what chapters are in what books anymore. So it would have been in chapter 8, the solutions chapter. And when we were talking about how maybe I didn't actually cover how to write total and net ionic equations with acid-base reactions for you guys. Maybe we just did precipitations, and that's where that is coming from. So do you, Renee, do you remember us talking about total and net ionic equations for precipitation reactions?
No, but there was Alex homework on it, but I just read
I
the
know we
explanation.
covered precipitations at least. So
Would that have also been chapter 8?
yes, absolutely.
Okay, let me look. Hang on just a sec.
Or maybe I just decided not to cover that at all this time. If you guys, I trust you for not remembering this. So if that was one of the things I decided just not to cover, I don't think that total and net ionic equations are covered in the textbook to the same extent that I normally cover them in class. Check it.
I remember seeing them in one of the labs. But I kind of used like Khan Academy and like other resources to like kind of teach myself how to do some of those questions.
Yeah.
And this seems more like the chapter 9 homework, if anything.
Well, this has to do with chapter 9 because chapter 9 talks about reactions of acids and hydroxide bases. So, so since I guess we didn't cover how to write total and net ionic equations enough, that kind of sucks because that was in one of the labs. I thought I covered it, and if I didn't, that means that I've got to like go back and make some allowances for the fact that people probably didn't do as well on that lab as they should have because I didn't tell them how to do it. That sucks. I guess don't worry about this question for the exam. So I'll make sure that that doesn't show up anyplace since it doesn't look like we covered it. Because I'm looking back through my class notes also from all of our lecture times, and I'm not seeing any examples of this anyplace.
Yeah, I was freaking out. I was like,
No,
oh
it's
my
totally
gosh.
fine. So normally I do cover this, and I think my thought process was it's not in the textbook. It is something that's sort of useful and fun to learn about because it's a good way for us to think about how to simplify reactions to their like simplest forms. But I also wanted to try and cover more of chapter 9 this time than I normally get to. And we did that. So I guess this is what I took out so that I could have more time to get to chapter 9. So don't worry about question 21. You're not going to have an exam question like that.
Okay.
All right. And I'm writing a note for myself right now. All right, that's my note to myself. Hey, self, don't write one of those for the exam because the students are going to be mad at you. And now I've got to go back also and look at that lab with total and net ionic equations in it because I messed up if we didn't cover those because normally I do cover them. So I guess I wish people had told me, hey, I'm having struggles with this lab because you haven't taught us how to do this. I would have taught you how to do that then. I never want you guys to feel unsupported for learning. So I screwed up. I didn't mean to, but I did.
Could we please look at 25?
Okay.
I realized when I took notes on that on the recitation, I put a lot of the equation shifts, but I didn't elaborate on which direction.
Yeah.
And so I'm kind of confused as to what all that means.
So this is your Le Chatelier's principle question. So you guys can see that balanced equation. We have 2 solid carbons plus O2 gas is in equilibrium with 2 carbon monoxide gases. and the delta H for the reaction is negative. That's important.
It's an exothermic reaction.
It is, yeah. And that's why the delta H is important, because the fact that it's an exothermic reaction tells you something about how temperature is going to affect the equilibrium. So first of all, if we're writing the general expression for KEQ for this reaction, remember writing a KEQ, we're going to do products over reactants. The coefficients from the balanced equation become the exponents in the KEQ expression. So we should have our molarity of carbon monoxide squared divided by our molarity of O2. Note that carbon doesn't show up in the equilibrium expression because it's a solid. Only gases and aqueous concentrations show up in equilibrium expressions. Solids and liquids do not. That's also important. Okay, so Le Chatelier's principle tells us that whenever we disturb a reaction at equilibrium, the reaction will act to counter the disturbance. In other words, whatever we do to mess up the equilibrium, the reaction is going to try and do the opposite to unmess it up. Whatever we do to the reaction to mess up the equilibrium, the reaction is going to try and do the opposite thing to unmess the equilibrium. All right, so what are we doing to mess the equilibrium in the first part? We're removing carbon monoxide from the reaction container. We're taking some products out. So if we take products out and mess up the equilibrium, the reaction is going to try to respond by making more products to replace the ones that we took out. So in other words, the reaction will shift toward products to make more carbon monoxide to replace the stuff that we took out.
Sorry, Dr. Mess, could you please repeat when you said when you take products out, the reaction tries to what?
To make more products to replace the ones we took out. So if we take away some products, the reaction is going to try and do the opposite, which is making more of those products. Does that make sense? Silence.
Yeah, that makes sense.
That makes sense. I copied down the table that I think was in our textbook. I have it like here, like in my notes, and I've used that to kind of like study off of. So you like can see that.
Is there a
Oh,
table for Le
that's
Chatelier's
great.
principle in your book?
Yeah, I think you added it to one of the videos as well, and that really helped.
I'm not a huge fan of a lot of the tables in the book, but I mean, everybody has a different learning style. So if it
Yeah.
works for you, then use it. That's fine.
My brain like needs like organization.
Well, to me, like my brain needs a first principle, and that's where I get my information from. So Le Chatelier's principle, the basic principle is where I think through all of these problems from. Like whatever we do to the reaction's going to try to do the opposite thing. So if we take some of this away, the reaction's going to try and make more of this thing. So how can this reaction make more of this thing? It can do it by shifting to the right to make more products. All right, so it's making products to replace the ones that we took away.
Okay,
Now,
so I'm sorry. So how is it a shift? How do you determine shift? Like, why is it because
so
there's
shift
less?
just means that if the reaction was at equilibrium, the reaction is going to push to the right to make more products. So shifting right just means that we're going to make more products to get back to equilibrium. Does that make sense?
So by the right, in this case, it means to the products.
Exactly. Right
Okay.
always means products. Because based on convention, we always talk about the things to the left of the reaction arrow as the reactants, and the things to the right of the reaction arrow as products. So another way of saying it's going to make more products to get to, or another way of saying it shifts to the right is to say it's going to make more products to get back to equilibrium. So that's another sentence you could use to describe what's happening here. Does that help, Renee? I guess not, since you didn't say anything back.
Sorry, I was nodding. Yes, thank you.
Oh, you're welcome. I can't see you right now because my screen is covered up in
Oh,
Windows.
so sorry. Okay.
Okay, so what about part B? What if we add more carbon into the reaction container? This is hard. The reason why it's hard is because you're adding more of a reactant, but this reactant is a solid. In other words, it is not part of that equilibrium expression. It doesn't affect our equilibrium balance between products and reactants. The carbon has to be in there for the reaction to happen, but it does not affect the equilibrium of the reaction. So adding more carbon wouldn't have any effect on the reaction at all because it's not a part of the equilibrium expression.
Okay, so but can we say, for example, what if we were to add more of oxygen? So the product that is able
if
to
it's
affect the
gaseous, okay.
equilibrium?
So what if we added more O2? That is part of the equilibrium expression. So we screwed up the reaction's balance because now there's too much O2 in there. Does that make sense, Renee?
Yes.
So if there's too much O2, the reaction's going to respond by trying to get rid of some O2. How can this reaction get rid of O2? It can do it by turning O2 into products. So the reaction would shift to make more products to get rid of some of that O2.
I guess it just seems kind of strange to me. I mean, I understand the words you're saying, but strange that if you're removing something on one side or adding, well, I guess it's the same thing. If you're removing a product and adding
Right.
Oh yeah, and
removing
adding a
some of
reactant,
product or adding extra reactant do the same thing.
It's the same thing. Okay.
Yep. So if we added more carbon monoxide, so we had too much, the reaction would shift to the left and make more reactants to get rid of some of that carbon monoxide that we added.
Got it.
Is that a
And
little
then
clear?
carbon's not a part of that equilibrium because
Because it's a solid.
because why again?
Because it's a
It's a
solid.
solid. Got it.
Solids and liquids do
Okay.
not show up in the equilibrium expression. Because equilibrium
Got it.
expressions always talk about molar concentrations of things, it's hard to even define what the molar concentration of a pure solid or a pure liquid is. And those numbers are constants anyway. So they don't show up in the equilibrium expression because the actual molar concentration of a solid or a liquid is a constant.
Mm-hmm.
So basically, if it's a solid or liquid, it doesn't show up in the equilibrium expression. That's what we need to remember.
That makes sense.
Okay, so what if we lower the temperature inside the container? What's that going to do to the equilibrium? Well, in order to understand how this equilibrium responds to temperature, we have to remember that this is an exothermic reaction. A delta H of negative means exothermic. So in other words, heat is a product of this reaction. If we lower the temperature in the reaction chamber, whatever we do to the reaction's going to try and respond by undoing that thing. If we lower the temperature in the reaction chamber, the reaction's going to try and make more heat to increase its temperature. So how can this reaction increase its temperature? It can make more products, because when it makes more products, it also makes more heat. Now, Renee, what if instead we increased the temperature that we were doing the reaction at? In that case, we've added too much heat, or more heat than the reaction needs at equilibrium. The reaction's going to respond by making more reactants, because when it makes more reactants, it uses up heat. Does that make sense?
Yes, thank you.
Yep. And then finally, what about if we increase the pressure inside the container? Now remember, increasing the pressure, in order to get back to equilibrium, the reaction would have to decrease its pressure. So whatever we do to the reaction's going to respond by trying to do the opposite thing. So this reaction would need to decrease its pressure to get back to equilibrium. How can this reaction decrease its pressure? Where does pressure come from? It comes from the number of moles of gas in the container. So this reaction can shift to decrease its pressure by shifting to whichever side has less moles of gas. And it looks like the reactants only have 1 mole of gas and the products have 2. So if we increase the pressure, the reaction's going to respond by shifting to make more reactants, because when it does that, that allows the reaction to decrease its pressure.
Can you just go over that last part again? Just repeat yourself.
Okay, so where does pressure come from? Pressure comes from collisions with the walls of a container. The more moles of gas we have in a container, the more pressure. Does that make sense?
Yes.
Okay, so what we've done to disturb the equilibrium in this last part is we've increased the pressure in the container. We've squeezed the reaction. So if we increase the pressure, the reaction's going to try and get back to equilibrium by decreasing its pressure. This reaction can decrease its pressure by shifting to the left, because the left side of the reaction only has 1 mole of gas in it, and the product side has 2 moles of gas in it. So we shift to the side of the reaction that has less moles of gas, and by doing that, that's how the reaction decreases its pressure.
Okay, thank you.
You're welcome. This is one of those things that I teach, and it's weird to me because maybe I've just been doing it for long enough that it has become second nature. But students really struggle with this, and to me, it's like super obvious, which I'm not trying to say that to be dismissive at all, but it's hard for me to like come up with 100 different ways to explain this, because the words that I use are ones that I understand really well. So I'm trying to come up with different ways of saying the same thing so that something will stick with you guys. But this is something that's hard for me to teach well, I guess. I got to start watching more YouTube videos and find 10 different ways to explain this. So maybe one of them will resonate better.
Well, especially like with the pressure, I would think that you would have to actually eliminate, something from the reaction as opposed to just looking at the moles involved. Like I wouldn't have thought of
Yeah,
that.
but you don't have to. Isn't that weird? Based on that, I mean, in this reaction, the products have more moles of gas than the reactants do, right? So it's not just total moles present, because in fact, the reactants actually have 3 total moles of stuff and the products only have 2, but pressure only comes from moles of gas. So because of that, the reactant side has less pressure than the product side. All right, if we shift to the left, we decrease our pressure. If we shift to the right, our pressure increases. So in this case, to respond to an increase in pressure, the reaction shifts to the left to decrease its pressure in response.
I had a question on 9.
From the
I
practice
feel like
test?
I have been struggling with, yeah, so it's gonna be, yeah. I feel like I always miss things,
yeah.
like little like
So this
details
was-
on
Okay, so this was in the topical videos, but I'm not sure whether we discussed this during a recitation or not. So let's talk about how intermolecular forces relate to boiling point. It was definitely in the topical videos. All right.
Okay.
But
Sweet.
let's review it here also, so that makes sure everybody sees it. Okay.
Mhm.
Okay, so Meadow, first of all, if we're defining what intermolecular forces are, they're the forces that hold separate molecules together, attractive forces between molecules. And when we covered the types of intermolecular forces, our strongest type were hydrogen bonding. And then in the middle, we had dipole attractions. And then our weakest kind, I think your book refers to them as dispersion forces. I like to call them induced dipole attractions because that's a descriptive term, but whatever. Those are the kinds of intermolecular forces from strongest to weakest. So what I want to do is I want to look at an example of 3 molecules, one of which has each of these types of forces. And the other important thing is that all of these are relatively close to the same size as one another. So water is our classic example of a molecule that has hydrogen bonding for its type of intermolecular forces. For dipole attractions, we'll use formaldehyde, CH2O, and then CH4, methane. That will be our example of something with dispersion forces. So what I want to look at is let's look at the boiling point for each one of these. Now, water, we already know its boiling point. So water boils at 100 degrees Celsius. Now we're going to do some quick Google searching and see the temperature at which formaldehyde boils. So remember that the Lewis structure is really important for us to figure out what type of intermolecular forces. Water has hydrogen bonding because it has one of those special hydrogens with a covalent bond to oxygen or nitrogen or fluorine. So that makes this hydrogen, or both those hydrogens, very, very delta positive. So they form super strong attractions to an electronegative oxygen or nitrogen or fluorine on another molecule. All right. So that attraction between molecules, that is hydrogen bonding. Formaldehyde has a Lewis structure that looks like this. If we add up all of the bond dipoles in that molecule, the big one is the carbon-oxygen dipole because oxygen's much more electronegative than carbon. So our net dipole points toward oxygen, which means the oxygen side of this molecule is slightly negative. The hydrogen side is slightly positive. These hydrogens are not those special superhero hydrogens. They cannot hydrogen bond because they are not covalently bound to oxygen or nitrogen or fluorine. But the delta positive side of one formaldehyde can form an attraction to the delta negative side of another formaldehyde. So that's an attraction between oppositely charged dipoles. That is dipole-dipole attraction, all right? Our medium kind of intermolecular forces. And then finally, when molecules of methane attract one another, methane is completely nonpolar, which means that there are no places that are permanently delta negative or delta positive around methane. But when the electron clouds of 2 methanes get close enough to one another, they sort of push each other out of the way a little bit and create these very small temporary dipoles. All right? Those dipoles are not there all the time. They're only there when those electron clouds are close enough to interact with one another. We call them induced dipoles. So the attraction between the induced dipoles on nonpolar molecules, that's what dispersion forces are, the weakest kind of intermolecular force. All right, so now that we know strongest to weakest, what our intermolecular forces look like, let's look at how the boiling points of these compounds correspond to that. So I'm going to look at the boiling point of formaldehyde. Let's make sure we keep the correct units. All right, in degrees Celsius, formaldehyde boils at negative 19 degrees Celsius. So it's a gas at room temperature. All right, now that means that in order for formaldehyde to be what we use to embalm dead people, it's not just formaldehyde, it's actually a solution of formaldehyde in water. That's what we use to embalm dead people with. And then for methane, let's check it. Woo. Now, on a really cold winter day, someplace other than Western Washington, well, I suppose we could get to negative 19 degrees Celsius here, but that would be like record cold, right? So very, very cold. Negative 161.6 degrees Celsius, that's like dark side of the moon cold. So we never get that cold on Earth. So now that we've looked up the data, why don't you guys tell me what you think about how boiling point corresponds to intermolecular forces? That's the data. What can we say about the data?
As you go from the weakest to the strongest, the boiling point needs more energy, needs more temp to boil.
So in other words, as our intermolecular forces get stronger, our boiling point goes up.
Yes.
Yeah, that's it. That's
Okay,
exactly right.
That makes sense.
And that the reasoning behind that, Logan, is exactly like you said. So in order to boil, what has to happen is we have to take these molecules that are attracted to one another in the liquid state and break those intermolecular forces to move the molecules into the gas state. So of course, it's going to take more energy to boil water because we're breaking stronger intermolecular forces to turn liquid water into gaseous water. All right? It doesn't take very much energy at all to turn liquid methane into gaseous methane because the attractions between methanes are really weak anyway. It doesn't take us a lot of energy to break the intermolecular forces in methane to have it go from the liquid state into the gas state. The same thing is true with melting points as well. So melting points track with boiling points. In other words, the stronger your intermolecular forces are, the higher your melting point is also, for the same reasons. Meadow, is that helpful?
Yeah, that was really helpful. That helped me on question 8 too. And then
Sweet.
the answer for question 8 would be C, correct?
I don't know what question 8 is, but I'll look at it.
Yeah. I just like to make sure I get things correct. It gives me peace of mind.
Remember, the answers are never as important to me as the principle. A is C.
C. Okay, perfect.
What is an ion dipole?
That's an attraction between an ion and a dipole.
Okay.
So in other words, one great example of an ion dipole attraction is what happens when ions dissolve in water. So if we had a bromide ion dissolved in water, the way that would be surrounded by water molecules is that those delta positive hydrogens would form an attraction to the fully negative bromide ion. This is an attraction between an ion and a dipole because that hydrogen is delta positive. That's an ion dipole attraction right there.
And I'm guessing in this, the strength category, it would be between induced dipole and dipole-dipole.
Actually, this is not an intermolecular force because this isn't a molecule, it's an ion.
Okay.
So that was intentionally put in there just as a misleading answer. It exists, but it's not a type of intermolecular force, at least not with pure molecules, because we don't normally have ions within a molecule. Now, it can be true, But in order for that to be true, we have to have something with a negative or a positive charge. We just didn't talk about examples of ion dipole forces anywhere. All right. So in terms of intermolecular forces, the three kinds that we talked about are the important kinds. In terms of strength, ion dipole forces can actually be stronger than hydrogen bonding. If not, they're in the same league. Okay? You guys are so quiet. It's scary.
I'm focusing.
That's fine.
Same.
We can see each other, so I forget that you can't see like us nodding.
Yeah, the problem is, like, I have one 14-inch monitor. In order for me to see everything big enough, I can't have you guys taking up a third of the monitor, so I just use the windows. And
Yeah, it makes sense. That's good to know.
what else can I help you with?
11.
11.
I needed help with that one too.
So we talked about this in the solids portion of solids, liquids, and gases from chapter 7. When we're talking about ionic solids, always we see what happens is that if there's one positive ion, it's always attracted to multiple negative ions. And each negative ion is also attracted to multiple positive ions. So that picture, the shape looks actually like a lattice from a garden. The example that I gave in recitation was with sodium chloride, which looks sort of like this. So this is my crummy version of the picture. In that picture, each Na plus is attracted to multiple chloride ions. In this case, I'm showing 6 of them around each Na plus. The formula of NaCl is NaCl. In other words, there have to be just as many sodiums as there are chlorides. Now that means that each chloride ends up having attractions to a total of 6 Na pluses. So if we keep on extending this picture.
Dr. Musk, are you wanting?
Oh, sorry, I forgot to screen share.
You have
Damn
to
it.
look at your document camera.
I forgot to share my screen. Sorry. I'm just drawing anyway.
No worries.
So each Na plus is surrounded by multiple chlorides. Each chloride is surrounded by multiple Na pluses. If we keep on extending this picture, it actually forms this three-dimensional version of like something that we would maybe like have in our garden to grow tomato vines on. This looks a lot like this, a lattice. Wow, my pen is dead. So this structure is nicknamed for like a lattice that you would find in a garden. All right. It's just what scientists saw when they looked at this structure where each positive ion is surrounded by multiple negative ions. Each negative ion is surrounded by multiple positive ions.
What would a network look like?
An ionic lattice. So networks solids are a covalent kind of solid. This is not covalent, this is ionic, all right? Network solids have an extended network of covalent bonds. For example, graphite was one of the two that we talked about. We talked about diamond and graphite, 2 forms of carbon. So in graphite, each carbon in the structure is bound to 3 other carbons. Each carbon in the structure is trigonal planar in shape. So if all of these carbons are trigonal planar, then that means that all of these carbons, and we just keep on going. We can get bigger and bigger, all right? We could draw the entire page and then another 1,000 pages in each direction. And all those carbons would be in an extended network and would be connected by covalent bonds. Now, because all of the carbons are trigonal planar, that means all of the carbons in this sheet of graphite are in the same plane. Now, this is one of the last things that we covered before we started talking about acids and bases. It's in one of our last recitations. So I promise today I'll go through and tag the remaining recitations that I haven't with the topics that were covered in them. And that'll help you guys because this is in those if you weren't there for that day, okay? So this is one of our examples of a network covalent solid. Network covalent solids are solids that have an extended network of covalent bonds. Now, when we look at graphite structure, the cool thing about it is the fact that all of the carbons are trigonal planar, that all of those atoms are in the same plane, actually influences the properties of graphite a lot. Graphite is formed in sheets. And if we have lots and lots of those sheets next to one another, they can slide past one another. So what that means is that graphite actually works very well as a dry lubricant, because if we have bunches and bunches and bunches of sheets of carbon atoms in between two metal surfaces, when those two surfaces would have friction, instead they will just slide past one another because the sheets of graphite can slide and sort of take those forces instead. So graphite functions as a dry lubricant directly because of this structure where all of the carbons are in sheets. We also talked about another network solid, which was diamond. And in diamond, all of the carbons are tetrahedral instead. We're never going to finish, but we can keep on drawing in to make sure we have 4 bonds from each carbon there. So all the carbons in diamond are tetrahedral carbons. Now, because we have so many covalent bonds crammed into such a small space in diamond, that is what makes diamond so incredibly hard, all right? The fact that all those carbons are tetrahedral, breaking enough bonds to mess up diamond's crystalline structure is really difficult. So those were the 2 types of network covalent solids that we talked about. But defining what a network covalent solid is, it's any solid that has an extended network of covalent bonds. Logan, is that helpful?
Yes, yes.
Cool. Anything else I can help you guys with?
So for question 23, are we using the ideal gas formula for that?
I have to get to question 23 first.
Okay.
Yep, that's right.
Good deal. Okay, sweet.
So Meadow, I'll just tell you that there is a trick in this problem. The trick is that when we look at the ideal gas law is PV equals nRT. Okay. So in order for the ideal gas law to work, N is in moles. In the information that I gave you in question 3, I gave you a number of grams of O2, not a number of moles. So guess what? You got to convert your grams of O2 into moles to get that question right. Does that make sense?
Oh, okay, that makes a lot more sense because I was like, I wasn't sure if that was the right way to do it.
Yep. So other than that, you know everything in the ideal gas law there except for pressure. So let me just quick convert our grams of O2 into moles of O2. So I'm getting 0.86875 moles of O2 there. Now, how can we solve for pressure? And the other thing that's interesting is I didn't tell you, oh, I did. I said units of torr for pressure. So that's going to tell us what units we need to use in the ideal gas law for the ideal gas constant. So we're solving for pressure and we know everything else. Our volume is 27.2 liters. Our number of moles, 0.86875 moles. Our R, our ideal gas constant, with torr in it is 62.4 liter torr per moles Kelvin. And then finally, our temperature, we have to report our temperature in Kelvin, not in Celsius. So 177 plus 273, it's like 450 Kelvin is our temperature. So when I solve for my pressure and torr, I end up with 897 torr. This is definitely a plug and chug kind of problem. You know all the variables except for one, and you just solve for the one that you don't know by substituting. The wrinkle is that I didn't give you moles of the gas, I gave you grams, so you had to convert to find how many moles of O2 you had. That was the trick in that one. Okay.
And so we made sure it was in torr by, if you have to do anything.
By using the correct units for the ideal gas constant. So if I had asked you what the pressure in atmospheres were, then instead we could have solved this way. My liters still stay the same. My number of moles still stay the same. My ideal gas constant with atmospheres in it is a different number, 0.08206 liter atmospheres per mole Kelvin. So you just have to make sure that the units that you're using in R match up with what the units for pressure that you want are.
Got it.
Does that make sense? All right, we still got office hours from 1 to 2 today, office hours from 3:30 to 4:30 tomorrow, office hours from 1 to 2 on Wednesday. And we've got one more recitation tomorrow at 5 where you can ask any more questions that you want. So we've got time still. Remember also that all the assignments are fair game again. So if you haven't turned something in, turn it in and get those points. So I want you guys to all do as well as you can in the class. It's the best I can do to help. You still got to do the work though.
And we do have that recitation on Wednesday, correct?
On Tuesday. Tomorrow we have a recitation. On Wednesday, the
Yeah, on
exam is
Tuesday
already
and then on
gonna be-
Wednesday, or no?
Not on Wednesday because the exam period's already going to be open on Wednesday.
Oh, got it. Mm-hmm.
But I'll still have office hours that day. So if you haven't taken the exam yet and you want to talk about something, then that's fine. I don't care. All right, I'll be around. All right, if you guys got nothing else, then study hard and I'll see you tomorrow, hopefully. And if not, and if I don't see you before you take the test, thanks for your hard work this quarter.
Awesome. Thank you.